Summit 2022. I hope you are enjoying it as much as I am. My name is Corey Johansson, and I'm a senior software engineer at Verda.ai, and I'd like to talk to you today about what we have learned building a production machine learning model quality monitoring system using Apache Druid. Starting off, a little bit about me. I am a software engineer. I have been building software professionally for 25 years. In that time, I have worked on a little bit of everything, from embedded hardware to large-scale SaaS distributed systems. I'm not a data scientist. Prior to joining Verda, I had almost no idea what data science was. That makes this domain new to me. I have spent the majority of my career working in Java, but have shipped code in many languages. I currently work primarily in Java, but also spend a good amount of time in Golang, a language I begrudgingly admit that I like. Now, I joined Verda 2 years ago to build a brand new product. We wanted to create an automatic machine learning model monitoring system. But first, I was going to need to learn what that was. So what does this blob of words mean? All of this is based on machine learning models. So what are they? Now, machine learning is the application of artificial intelligence algorithms to solve problems. The learning model is built by training the algorithm on pre-labeled data until it can properly perform its desired job. Once trained, the model can be used to make predictions. Given a set of inputs, predict the output. For all of the mystique that surrounds them, machine learning models do exactly one thing: predict. These models are used for all kinds of things. They surround us. There are the obvious examples like suggesting ads for your social media feed and products you might like at your favorite shopping site. But there are also a lot of other examples you don't necessarily consider, like image recognition, spam detection, systems that monitor blood glucose levels and alert patients of pending health issues. For real-world prediction, the outcomes they produce need to be validated as correct. Model quality measurements are objective assessments of the performance of the model. These are just a few, but each of them has tremendous value. Precision and accuracy measure the percentage of predictions made by the model that result in canonically correct outcomes. Drift measures how differently the statistical distributions of the predictions compare to the data used to train the model. Outliers measure predictions that fell outside of the expected statistical distributions of the data and represent potentially new data points or new use cases. The combination of these metrics allows for the analysis of a machine learning model by empirical means and can be used to determine the source of change. Combining these ideas produces a new concept: model quality monitoring, the measurement and presentation of model quality metrics in a method suitable to allow data scientists to operate and improve their models. To create a product that can perform these tasks for a data scientist, the system must be capable of producing the necessary metrics. To achieve that, the system must be capable of automatically collecting the data from the predictions in the model, and the data must be efficiently stored in a highly available and fault-tolerant data store. The system must also be capable of aggregating the data stored and producing the aggregated output in a format suitable for product use. So let's say you wanted to build a system that can do this. What would you need to build? Data scientists are not engineers. They neither want nor have the time to write large amounts of code to obtain the measurements they need. They need a black box product that can integrate simply with their workflows. It must support the ability to ingest data in pre-computed batches or from live data models, producing predictions in production environments. The system must be fault tolerant, such that data is never lost, nor ingested more than once. There are a variety of data formats the data can already exist in that must be supported for ingest. Comma-separated values, JSON, Parquet, and Snowflake tables are all very common examples, and the user should be able to use the existing data as is. The data storage system must be flexible and needs to support general-purpose blob storage technologies. Now, realistically, this means S3 buckets, as they're just the most common, but other blob stores, if supported, are a huge bonus. Now, as this system scales, there will inevitably be a time at which data storage size becomes a concern. Therefore, the storage engine must support the ability to age out or roll up existing data over time. The measurements and metrics we need to produce are, in many cases, applications of standard statistical analysis methods applied to very large data sets. The query engine for the platform should provide as many of these as possible out of the box. Now, we also know that we have a set of metrics that are specific to our domain and need that platform to provide methods by which we can build and execute them. And since we are talking about potentially vast quantities of data, the query engine needs to be smart and leverage distribution for accuracy. What if some amazing group of developers out there had already created a system that would do this job for us? As it turns out, those awesome developers are real, and they build Apache Druid. Now, previously in my career, I worked in application performance monitoring, or APM, a domain in which time series data storage and aggregation are actually very core technologies. I had spent years working with distributed query engines, and I knew that technologically that was going to be the right solution to the problem. So we designed an architecture for our product that we felt would address all of our core needs. From what we identified, we found it was going to be a 2 to 5 year development cycle to build, just the core platform. Then we decided to compare our solution to anything existing that might reduce the work. That's when I first learned about Druid. When I started researching Druid, I was actually astonished. It looked like the platform supported nearly everything we needed and was already mature enough to adopt. It even has good documentation and an amazing user community. But I am a grizzled old engineer, and therefore I am unconvinced. I doubt all technology will do what is promised until I see it happen. So we decided to evaluate the platform for our use case and see if we had a match. Collection, how does Druid match up? Batch ingestion is a done deal. There is built-in support for the 3 data formats we needed the most, CSV, JSON, and Parquet, but there's also a lot more. The API is clearly documented and is easy to use. There are core extensions that enable consumption from Kafka and Kinesis. The consumers support all the features we would need to scale up reliably without risking data loss. The API is well documented, and configuring ingestion supervisors is pretty easy, all things considered. This is Kafka we're talking about. One thing we identified early on was schema fluidity. The data types for a model feature can change over time. Now, Druid provides different methods to support this, but for our purposes, storing everything as a string allows us to maintain the schema data types externally and version them over time. For situations in which the schema is invariant, we can leverage that and strongly type the columns for more efficiency. The use cases we were designing for all had a commonality. The data was time-based. Whether it is batches of data arriving on a schedule or real-time predictions running on a production endpoint, the data has an inherent time domain. Ultimately, we will produce charts and evaluate alerts that look at specific time windows, so time is a primary index. Druid is a time series analytics database and uses the timestamp as the indexing value. This carries with it a query language that is designed with time as the primary domain, allowing us to rapidly build the query interfaces we would need to represent the data we need to fetch. Druid has default support for deep storage to a wide variety of blob stores. As I mentioned, S3 is a primary technology in use, but the fact the platform already supports the others eliminates a risk and allows us to support environments using alternate blob store vendors. Druid supports the definition of retention rules and automatic data rollup to help manage the growth of the backing store. Having worked in systems that did not provide this, I can assure you it is extremely valuable. Anyone that has ever owned an Elastic cluster can tell you all about how important this is. Out of the box, Druid provides a pretty incredible selection of aggregation functions. The standard function library is surprisingly rich and covers a huge number of use cases. On top of that foundation, the system supports multi-value columns that can be processed and aggregated like vectors. This is extraordinarily powerful. With the inclusion of a core extension, the platform also provides high-precision statistical analysis methods. It's hard to overhype this. Building these aggregators from scratch is error-prone, so having a solid, reliable, pre-built set of core functions is a huge bonus to us. We knew going in that some of the calculations we need to perform would be custom. Druid provides an API for creating extensions, and with a bit of time and effort, we built a library of our own aggregators that produces the metrics we need from the raw data. There's more! Druid comes with a lot of stuff for free that is really unexpected. There's a web UI that I can and do use to administer and monitor operations. I literally always have at least one tab open in my browser with the Druid UI running in it. The native JSON query language, while occasionally a bit obscure, does work really, really well. It's highly amenable to access via libraries in multiple languages and allowed us to integrate with our own aggregations really simply, since we also use Jackson for serialization in our other Java backends. There's also an extension that enables metrics for Prometheus scraping, which we leverage via Grafana to produce dashboards for our Druid clusters. Those metrics also drive alert policies that we can use to support our product. We needed the ability to adopt metadata storage for different vendors. The existing support and extensions covered our needs, allowing us to run on multiple customer environments that use different backing databases. The administration of the entire system exposed via REST API. We have integrated our product system with that API, allowing our architecture and Druid to function as one large integrated distributed system. All this, good documentation, and there's even a great user community to support the platform. At this point, we decided we're going to use Druid. All this together. Druid is a very powerful time series analytics database, but is not a machine learning model monitoring system. What all do we need to do to get from where we are to that? There are some core requirements we discovered through experimentation that would be invariant. First, we needed to record absolutely everything. For every prediction the model makes, we need all of its inputs, all of its outputs, and a set of core tags and labels that we use to identify the data. For a model that is served by a live endpoint in a production environment, this could be millions to billions of predictions per minute. Some of these models have thousands of features, so this problem very rapidly can become very, very difficult to solve. All those predictions won't be terribly useful on their own. To measure drift, we also need to ingest the reference data. This is a sample data set, typically a subset of the data used to train the model, with a representative distribution of values in it. This data will be used to compare to predictions to calculate how far the distribution has drifted from the reference. Finally, to determine how accurate the model predictions are, we will need ground truth. Ground truth is a value typically provided by a human that says, for this set of inputs X, the output is Y. We use this data to compare the predictions the model actually made to what they should have been. An interesting aspect of this is that ground truth data arrives long after the predictions, days, weeks, months, sometimes even years later. That means the backing store needs to support backfill. It also means that pre-aggregation of the data at ingest is not viable, since we will need to re-aggregate at query time across the raw data to include late arriving data points. Druid can ingest our data, and we have a column model design that ensures we can read back and aggregate what we need when we need it. But where does this data actually come from, and how does it get to Druid? We will need a way to capture all of this data for each prediction and put it into a stream for consumption and ingest. To support general purpose ingest of batch data, we will need an API that customers can use to tell us where the data is, what it is shaped like, and optionally how to transform it as we ingest. We need to support arbitrary data batches in addition to well-defined data such as reference or training sets. Similarly, we need an API for customers to use to ingest ground truth. Ground truth does not typically contain the entire prediction. It is a compressed format that instead contains the ID of the prediction and the actual ground truth value. Our API is responsible for resolving the original prediction and decorating it with the ground truth value so that we can use that in aggregation. About custom aggregators for a variety of performance metrics: accuracy, precision, recall, F1, PR curves, ROC curves, histograms with variable bucket counts depending on data types, outlier detection, and drift calculation. Each of these metrics would need to be aggregated across time windows to produce time series visualizations, and we're going to need to do this on demand. Now, our platform manages the deployment of a customer's data model as an endpoint that can serve predictions. To get the most black box experience possible, we integrated into the deployment pipeline to automatically create Druid ingest supervisors and tasks for data batches. This also allows the customer to deploy their model, and the dashboard appears automatically. The user interface our customers use is designed to take our massive sets of aggregated numbers and turn them into charts that humans can understand. We had to build in a middleware layer that could build, run, and execute the queries against Druid and collate their results for return back to the user interface. Now, metric data is most powerful when it can be used to make decisions. Now, alerting is extremely powerful in this use case because it allows the user to specify the conditions under which they should be alerted, and then the system takes over responsibility of evaluating the data and triggering the alerts. The alerts will ultimately all be backed by queries against the data stored in Druid. So we know what all we need, and we know what Druid provides. Let's build a monitoring pipeline view of the overall architecture. Starting on the left in the middle, the machine learning model is the source of all monitoring data. Frequently, the model is used to process large batches of predictions. The pipeline provides an asynchronous method of ingest for the data batches that results in the data indexed into a Druid data source. When a model is deployed and servicing live predictions, the data is captured at time of prediction and dropped into a stream. At the other end of the stream is a consumer which reads the data payloads and indexes them into the necessary Druid data source. Users access the web user interface to view the monitoring data. A GraphQL middleware layer builds and executes the Druid queries we need and returns the results in a format the web app can process and display. In the middle of all of this is Druid. Capturing the live prediction data is core to supporting near real-time monitoring. It starts with a schema of the model. When the model is constructed and stored into our platform, it includes a schema that denotes the inputs and outputs and their types. We build a Golang proxy that wraps the ML model, capturing all of these inputs and the outputs from the prediction. Using its schema, it then validates it, creates a message payload containing the prediction and all of its metadata, and writes that message to a stream. If not provided in the prediction inputs, a prediction ID is also generated that will uniquely identify this prediction. We support batch prediction as well. An input batch is processed, and each prediction is assigned an ID and a batch ID. That data is ingested in the same manner as a single prediction into the same format. For each model in our platform that is deployed and servicing predictions, we maintain a supervisor that reads from a stream for that model. Initially, we relied on Kafka as it came operational out of the box. Eventually, we decided to move to Nat's Jetstream. This required me to write a Jetstream supervisor and a task that perform a similar but simplified lifecycle to the Kafka implementation. When an endpoint is deployed hosting a model, we automatically begin collecting monitoring data and sending it into Jetstream. And then we have a consumer on the other end inside a supervisor directly reading that data into Druid's data source and indexing. All of this complexity requires management. We build our architecture around eventual consistency, so one system is a source of truth on what the state of the universe should be. It periodically reconciles everything to match, creating and deleting supervisors as needed to match the models in operation. Data is a primary use case for us. At a minimum, we must support the ingestion of batches of reference data so that we can calculate, display, and alert on data drift. Reference data may be stored in a format with a different shape or naming conventions to the other data. During ingest, the user may optionally specify naming transforms that align the features across the data's origins. When we ingest the reference data, we instantiate those transforms and create dimensions that map the input data to the column model we maintain internally. The user provides the location of the batch file, such as an S3 bucket and path, and the format, so CSV, JSON, Parquet, whatever. Our platform creates the ingest tasks and sends it to Druid for asynchronous processing. Ground truth is typically abbreviated to only the ID of the prediction and the actual canonically true result. In order to associate this with the original prediction, we have to ingest the ground truth rows, resolve the original predictions, and then decorate them with the ground truth values. When we query the data back, we can see both the original prediction and the ground truth, allowing us to identify not only the number of incorrect predictions, but we can identify the actual predictions and all of their inputs, outputs, and metadata that go along with it. Live predictions from deployed endpoints are only one way to generate predictions. The other is batch processing, in which the model is run against a large batch of inputs and generates the outputs to some sort of storage. Ingesting these batches is similar to reference data, but with metadata decoration around identifying the batch. This empowers comparison across batches using the same aggregation techniques we use for live data. You can actually query it back. It isn't very useful. We have three major use cases for data query. First and foremost is the most visible, and that's the GraphQL layer that is we built in Golang that sits between our web app UI and our backend data systems. For populating charts on the screen, the GraphQL codebase builds and executes the queries against Druid and returns the collated results back to the web app for display. We also define alerts on the model features for every model. Whenever any drift and any feature exceeds a threshold, the alert fires to notify the user that the feature distribution is out of norm. Each alert is evaluated on a schedule and runs a Druid query to fetch the data that it is evaluating against. The evaluation takes place inside a Java service, independent of the GraphQL codebase. To build our queries, we use the Druidry, that's hard to say, Java library, with some extensions to support our custom aggregators. Since our architecture is designed around eventual consistency, we run a number of reconcilers inside the Java backend system that serves as our source of truth. Each one is responsible for ensuring that the state becomes consistent over time, and frequently they run queries against Druid to do this. The reconcilers share the same code base as the alert evaluation system, so they also use Druidry to build the queries they run. Additionally, some of these reconcilers create, destroy, or otherwise modify information in Druid surrounding supervisors, tasks, compaction, leadership, and other items. These interact directly with the REST API that Druid publishes to complete their operations. I would love to say we learned that this was easy, but that would be a lie. I would also love to say that we learned that distributed systems are hard, but in all honesty, I already knew that. We did learn a bunch, though, and as we built out the architecture and brought the system online, a lot of it turned out to be really valuable information. Our platform is built on and extends Kubernetes. We leverage as much of the underlying capabilities as we can, and we architect around the principles embedded in the Kubernetes design. That includes scaling horizontally, running stateless deployments, and running chaos instruments inside of our clusters. That requires every service to be highly available and fault tolerant. Stateless deployments and highly stateful systems don't like to cooperate. Kafka is a distributed database. Everybody loves it for stream processing, but it is a distributed database. Running Kafka in Kubernetes means allocating storage via persistent volumes and living with all of the problems that creates. If a Kafka pod is lost or cycled for any reason, the Kafka cluster is temporarily disrupted. This can lead to weird problems with consumers losing their offsets and simply stopping their consumption. Zookeeper is incredibly powerful, but unfortunately, it also requires the same type of volume storage. Since Zookeeper is used for node announcements, if anything goes wrong, the system just completely stops functioning. In particular, if a Zookeeper pod is lost or replaced, Curator gets very confused. The IP address changes when the new pod comes up, and very quickly the Druid nodes begin to lose contact because Curator is attempting to talk to the old IP addresses. There's also the very ugly problem of Kafka and Zookeeper filling up their storage volumes. Kubernetes does not allow you to resize a persistent volume. To get more storage, you have to delete the volume and the data it contains and create a new one of a larger size. That means you have to accept data loss because your drives aren't big enough. Ultimately, we opted to remove Kafka and use NAT's Jetstream, and we adopted the Kubernetes extension for node discovery. This allowed us to remove both Kafka and Zookeeper from our cluster. Designing for high availability and horizontal scale also changes how we allocate resources. Instead of one broker with 24 processors, we run between 2 and 12 brokers with 2 cores. We auto-scale up and down according to load. This means we have to use horizontal pod autoscalers. We have to define scaling policies, and we have to use Prometheus metrics to drive them, and we have to use pod disruption budgets to prevent outages. The Kubernetes extension replaces Zookeeper for node discovery with the Kubernetes APIs and pod labels. It's a great match for us since our architecture is built on and fully integrated with Kubernetes. So after I had a bad day with Zookeeper and a full disk, I configured the Kubernetes extension and I turned it on. And the thing is, it just worked. I literally did not believe it at first. Nothing ever works on the first try, and if it does, I automatically assume I did it wrong. But the thing is, I saw the coordinators get a leader assigned. I saw the nodes announcing, I saw supervisors running, and I was able to run our entire product. Everything was great. For 3 or 4 hours. Then things stopped working. Coordinator logs were full of null pointer exceptions and stack traces and errors, and it took me a significant journey into the extension source, but I did find and fix the null pointer, and I am running a modified fork of the extension in our production environment. We still see stale data accumulating in the coordinators due to the indexer pods getting removed and the extension failing to properly handle that during a leader change. The coordinator continues to try and contact the indexer to status check segments that are no longer there, and eventually it becomes non-responsive. So we just automatically cycle the coordinator pod every 3 hours. That means that leadership moves to another pod, and the new pod has no stale indexer addresses in memory. Now, I'm still working on isolating the exact circumstances of the error that we still see, so I can fix and commit upstream so that everyone running on Kubernetes can begin adopting it in favor of Zookeeper if they so choose. It's coming, I promise. I want to get it into 24 as soon as I can. Middle managers, but very quickly found ourselves constrained by resources. Middle managers spawn child JVMs for each task execution, which works well if you have large hardware. But if you are running on small hardware and scaling horizontally, it's very difficult to balance the sizing of each replica against the number of replicas you require. Indexers solve this by running the tasks inside a thread pool instead of child JVMs. Overall, this approach is dramatically more efficient with system resources. It also allows us to size each indexer much smaller and scale up as more ingestion pipelines are created. I would actually recommend this approach for everyone to switch from middle managers to indexers. They are a more efficient method. When we first were bringing the systems up, we cycled tasks very rapidly to leverage the indexer thread pools. I experimented with a large number of different task durations, and eventually I got it down to like a 1 minute task duration, and admittedly that is very, very short. But at that point, I noticed that the CPU consumption on the coordinator went through the roof, and query latency talking to it did the same. As it turns out, the chat frequency and task cycle times had begun to overwhelm the coordinator, and it was failing to keep up. Longer tasks with longer runtimes are better, and that's actually the reason that the default is an hour. I can assure you through empirical testing, yeah, an hour is a pretty good value for a task runtime. Auto-scaling the cluster to meet demand is surprisingly tricky. Kubernetes pod autoscalers support two metrics out of the box, CPU and memory. For the most part, these are decent proxies since the broker and router are mostly memory bound by number of concurrent queries. Historical nodes are also primarily memory constrained, so we can use that to scale. But concurrent queries and other performance metrics would also be really valuable. Indexers is the hardest because memory is a bad analog. They need to scale on task count. Ideally, I would size each indexer to run 8 tasks and then auto-scale according to the pending task count. To get this, we're going to need to construct appropriate scaling metrics and use them in Kubernetes. Fortunately, the metrics we need exist. They're in Prometheus, but getting them set up as pod auto-scaling metrics will require some engineering work. Thank you for joining me today to hear about my adventures with Druid, machine learning, and production. I hope you learned something, and I'd love to hear your questions.